Hello everyone, welcome to this week tutorial. Today's topic is four-bar linkage, position, velocity and acceleration analysis. In this video, we'll learn how to identify the correct linkage and relevant dimensions. Then we want to position analyze with the vector loop equations or vector loop approach. We'll also do velocity and acceleration analysis using the vector equations. So for four-bar linkage, now we have to fix pin joint O2 and O4. The link connected these two fixed pin joint, we consider them as link 1 or ground link or fixed link. The name suggests that they don't move, and for this example the theta 1 is 0 or the angle relevant to this link is 0 to make it simpler. Then we have link 2. Usually link 2 is considered as input link. You'll give an information whether link 2 is an input link or not. So how we can get the information? Either you'll give and that clearly mention that input link is link 2, or you'll give an angular movement of relevant link, and from that information we identify which one is link 2 or input link. So in total we consider input link as link 2, and the length of this link 2 is A. Then next one is link 3. We consider is at coupler link, and the length of this link we consider as B. And the next one is output link. We consider it as link 4, and the length of this link is C. And finally the ground link length we consider as D. So even though we start the numbering of link from ground, but when we denote the length A, B, C, D, we start from input link. So input link, coupler, output link, and then ground. So here you can see the link 2 input link is A, link 3 coupler link is B, and link 4 output link is C. Finally link 1 ground link is D. Now according to definition of the vector, we measure angle at the root of the vector with positive x-axis counterclockwise. So the angle that makes with link 2, we say them as link 2 theta 2. The angle that makes with link 3 we call them theta 3, and angles that makes with link 4 we call theta 4. And you can see from this diagram that theta 1 is 0 to make the diagram a bit simpler. Okay, let's look at this diagram and identify which one is fixed link, input, coupler, output link. To look at this diagram, I identify that this point and this point are fixed, so the connecting link should be fixed link. So this is link 1, ground link, or the length of the link should be D. Then the blue one, I can identify from this diagram that the blue one is moving, or blue one is the driver. So we consider this blue small link as link 2, input link whose length is A. Next is this is output link. From this diagram we clearly understand that this is output link. So the connecting link with input and output we consider as coupler, which is link 3, and the length of the link is B. And finally this is output link, link 4, output link we consider as C. And the extension part of the coupler, the pin joint here, we consider this is an extension part of the link, or if we consider this joint, this point, then we can consider a point on a coupler. Okay. Alright, so when you ask to analyze position of a four-bar linkage using vector loop method, then we need to follow 5 steps, usually 4 steps depending on the question. We need to do the step 5. And so in step 1, you're given these 3 equations which are link ratios. So you just identify correctly the link length and then you calculate this value, which all the dimensions will be given to you. What you need to do, you just use these equations and you identify K1, K2 and K3, which is in step 1. In step 2, you need to identify parameters A, B and C. Once again, all the values will be given to you considering theta 2, which is input link, and input link is always given to you. So once we calculated K1, K2, K3 and ABC, in step 3 we'll calculate theta 4. Once again, this equation will be given to you. Before we use this equation in step 3, we need to identify whether we consider the given system is open configuration or cross configuration. What is open and cross configuration? Let's look at that. So for open configuration, there are a few assumptions we need to fulfill. First of all, we need to check whether the 4-bar linkage satisfies Grashof condition or not. Then we need to identify the input link, whether it's in first quadrant. That means whether it's less than 90 degrees. And then we need to identify the smallest link. Once we identify the smallest link, then we look for 2 adjacent links to that link. So the adjacent links of the smallest link, if they do not cross each other, then we say this is an open configuration. If they do cross each other, then we say this is cross configuration. So according to that definition, we can look at this diagram and identify that this is open configuration because the angle is in first quadrant, this satisfies Grashof condition, and the shortest link is D, and the adjacent link to this D is A and C, and they do not cross each other. So this is open configuration, where this is cross configuration because A and C crossed each other. Okay, so if we just look back to this diagram once again, so depending on the position of the input link, we can get open configuration or cross configuration. So once again, before you identify or calculate theta 4, make sure you know which configuration you're considering for theta 3 and theta 4. Alright, so for theta 4, when we calculate theta 4 and when we identify that we are considering open configuration, so then the equation will be considered for negative value in between these negative b square minus 4ac, and if it's cross configuration, then we consider here this positive sign. So negative sign is for open, positive sign is for crossed. Once again, this equation will be given to you. You just need to remember which sign you need to consider for which configuration. In next step is step 4, where you need to identify theta 3. Now for theta 3, you can use 2 equations. It is recommended that for open configuration, use the first equation, which is a sine component, and from that equation you get the theta directly for open configuration. And for cross configuration, you use the second equation, which is a cosine component, and from that equation you get theta 3 directly for cross configurations. You can use the either equation to calculate theta 3 and theta 4, but it is highly recommended that you use the first equation for open, the second equation for crossed. All right, so that was the up to step 4. That was for velocity. My apologies, that was for position analysis. If you're asked to find transmission angle, then you need to definitely identify theta 3 and theta 4, and by definition you just take their difference, and that will be a transmission angle. If the transmission angle is less than 90 degrees, then that would be your final transmission angle. If it's not, then you have to subtract that angle from 180 degrees to make it accurate, and that would be your answer. And another thing to remember, that whether you consider open configuration or closed configuration, their transmission angle will be always same, even though their theta 3 and theta 4 are different. Alright, next one is for velocity analysis. So for velocity analysis, you'll be asked to identify angular velocity, and you'll be asked to calculate linear velocity. Let's start with the angular velocity first. So for angular velocity, the equation will be given to you. What you need to do, you need to identify the dimensions, and you need to calculate it before you start this equation, and the result will be radian per second. It's pretty simple. Before we identify the linear velocity of the 4-bar linkage, we need to just remember a few basic stuff. One is that if we want to convert from polar to Cartesian form, we can use Euler identity, and this is the diagram which represents the x coordinate. The horizontal line represents the real part, and the y component or vertical line represents imaginary part. And this a is it should be O. So OA is a vector which we can denote as R, and it makes angle with positive x-axis counterclockwise theta. So then we can represent that vector as a position vector as R ej theta in a polar form, and in Cartesian form we can write down R cos theta plus R j sin theta. So that is very basic stuff we need to remember, because for linear velocity, what you need to do, you need to derive the equation, and then you need to calculate for individual pin joints. So once again, if we just consider that OA is a vector which makes angle theta, and the length of this vector is R, then we can represent that position vector of the link OA as R, uppercase R equal lowercase r ej theta, and we can convert this as R cos theta plus j sin theta. To get the velocity, what we need to do, we need to differentiate this R with respect to time. So let's differentiate this part with respect to time. That makes R. Then we different R, because we keep R and we keep R aside because R doesn't change with time. Then we differentiate ej theta, and then we find j ej theta, and then we differentiate d theta by dt. But according to definition, that angular velocity is angular position with respect to time, so we can write R omega j ej theta. So that is our polar form for velocity vector. If we want to convert it to Cartesian form, that becomes R omega j cos theta plus j sin theta. Now we want to make it simplify, multiplying j. When we multiply this term with inner side, then we get j square sin theta, which makes j square is -1, so we get R omega in parenthesis negative sin theta plus j sin theta, j cos theta. So this would be our generalized linear velocity equation, where we can find that linear velocity of any vector or any link can be represented as the length of that vector, angular velocity of that vector, and a position or angle of that respective vector. So if you are asked to find VA, which means you are asked to find velocity of pin joint A relative to O2. Because O2 is a pin joint, we omit that part, so we can write VA. And because this is related to link 2 vector, so we take angular velocity, position, and length of that vector, so it becomes A omega 2 in parentheses negative sine theta 2 plus j cos theta 2. What about pin joint B? So for pin joint B, once again we consider that pin joint velocity, linear velocity of pin joint B relative to O4. Once again, O4 is a pin joint, so we omit that part. That becomes VB, and we can understand from this diagram that this is related to output link, so we put all dimensions related to output link. In case of coupler, where we can identify linear velocity of pin joint B relative to pin joint A, and then because they're A and B both are moving, we are not actually omitting any part, so we can identify from here that this is a linear velocity of B relative to A. And we can identify that from this diagram that this is related to coupler link 3, so we put all the dimensions related to that link. Okay, so now P is a point on coupler. When we add A and P, it makes a vector AP, and the length of this vector is given to us as RPA. So when we want to get the linear velocity of this pin joint, or the linear velocity of linear velocity of AP vector, the expression would be the length of this vector, which is RPA, and then angular velocity of respective vector. Because P was a point on the coupler or link 3, that's why we consider omega 3. And with the angle, what once again definition, according to definition, would be the vector that makes angle positive x-axis counterclockwise. So if you just look at this diagram, that it makes angle theta 3 plus delta 3. Delta 3 is the angle between AP and AB, so that's why we consider this whole angle, and that's why we wrote delta 3 plus theta 3. And for your information, this RPA and delta 3, this information will be given to you. So when you are asked to find linear velocity of pin joint A and B, so you use this equation for pin joint A, you use this equation for pin joint B. And also when you're asked to find any point on coupler, which is P, then that would be not your answer. The answer would be VP equal VA plus VPA. So for acceleration analysis, if you're asked to find angular acceleration of the links, angular acceleration equation will be given to you. So what you need to do, you need to identify these 6 parameters A, B, C, D, E. Once again, all of this equation will be given to you, so you don't need to remember. One important thing to just remember, that you identify correct link length and respective angles. So that is the angular acceleration. Once again, if you're asked to find linear acceleration of pin joints at any point, then again, like the linear velocity, you need to derive the equation, and then you need to calculate respective pin joint linear acceleration. So for linear velocity, we found this expression in Cartesian form. If we want to differentiate this velocity with respect to time, then we have to differentiate this a few minutes ago. Then what we need to do, we need to differentiate is one more time. This time you can identify that R and J do not changes with time, so they are constant, but omega and theta varies with time, so there are two variables. So what you need to do, you need to differentiate with two variables, which applies UV relationships, where you can consider omega as U and EJ theta as a V, and then we apply that differential equation. So once again, when you differentiate this bit and then when you differentiate the omega with respect to time, we get alpha, which is a definition of angular acceleration, and then we put all the variable that we get, and then we simplified it. Once we are happy with the simplification, then we convert this polar form into Cartesian form, and we finally got that expression. By the way, you can definitely differentiate Cartesian form that we found here. You're more than welcome to differentiate Cartesian form of position vector, Cartesian form of velocity vector, but I find it really simpler to differentiate polar form rather than Cartesian form. So I differentiated a polar form and then converted to Cartesian form. So the general linear acceleration equation gives us like that: R, my apologies, there shouldn't be J here, so it should be R alpha. So R is the length of that link, alpha is the respective link angular acceleration, and then theta are the angles, and theta is the angular position of that link. Once again, omega is angular velocity of the respective link. Once you identify this general equation, then it's really easy to just put respective dimensions of the link, and then you get the value. So if we consider for pin joint B, as you can remember, it was relevant to output link, so we get all the dimensions relevant to link 4. If we consider AB or coupler link, we put all the dimensions relevant to link 3. And for AP, which is a P is a point on a coupler, and once again we need to get that dimensions, which is length is given to you as RPA, and P is a point on a coupler, so we need to get dimensions relevant to link 3, so that's why alpha 3 and omega 3. Alright, so that was position, velocity, and acceleration analysis. If we just recap very quickly, so for position analysis, you'll be asked to find theta 3 and theta 4, and to find that there will be 4 steps. In step 1 and 2, you need to identify link ratios and intermediate parameters. In step 3, you need to confirm whether you need to get theta 3 or theta 3 and theta 4 for open configuration or cross configuration. Once you identify that, then you need to use the equations to respective configuration and find theta 3 and theta 4. And for transmission angle, if you are asked to find it, feel free to find that value. From step 1 to step 4, all the equations will be given to you, so you don't need to remember these equations. For velocity analysis, you'll be asked to find angular velocity of coupler and output, as well as linear velocity of pin joint A, B, and P. So for angular velocities, equation will be given to you, so you don't need to remember it. But for linear velocity of pin joint A, B, and a point on coupler or any link, P, you need to derive the equation and then you need to get the values. Same applies for acceleration analysis. You'll be asked to find angular acceleration for link 3 and link 4 and linear acceleration for pin joint A, B and P. Linear acceleration equation will be given to you for angular acceleration equation will be given to you for linear acceleration. You need to derive the equation and then identify it. Some very useful tips is that first step would be to identify write A, B, C, D, which are the length of the links, and just remember that angle is always measured with positive x-axis counterclockwise at the root of the vector. If angular velocity positive, that means it is counterclockwise. If it's negative, that means it is clockwise. For finding theta 4, just remember from this equation that the negative sign is for open configuration, positive sign is for crossed configuration, and in case of linear velocity and acceleration analysis, you need to identify whether you get angles in third or second quadrant. If that is the case, you need to consider adding or subtracting 180 degree to make it positive x-axis counterclockwise at the root of the vector. Alright, so from this tutorial you were introduced the 4-bar linkage, the general definition of how to measure the angles and how to identify the link length. Then you're introduced the equations for position analysis, vector equations. Two type of equation, one will be given to you, the other type you need to derive for velocity analysis. Similar for acceleration analysis, angular equation will be given to you. For linear acceleration, you need to derive the equations. Thanks for watching.